In this unit, we're going to learn how to go about naming haloalkanes. Haloalkanes are also known as alkyl halides. And what we're going to see with haloalkanes, also known as alkyl halides, is that by definition, they will have a halogen that is bonded to an otherwise alkane molecule. So you'll notice in the example problem that I've drawn here below, we have a halogen atom, that is our chlorine atom, that is connected to a molecule that has otherwise exclusively carbon-carbon single bonds. So by the end of this segment, you will know how to go about determining the name of a haloalkane using IUPAC nomenclature. And at this point, if you're unclear or a little bit shaky on naming alkanes, you can go back and review videos number 14 and 15 from the YouTube library here, because those are the videos where we went through the guidelines for naming alkanes. So I'm going to assume as we go through here that you're really familiar with nomenclature of alkanes. Thinking of going back to that review of naming alkanes, we had the quick start guide to alkane nomenclature, and we're going to use that as our starting point here for naming haloalkanes, because all of the guidelines here are the same as for naming alkanes, except that rather than having just alkyl branches coming off of the chain, we will also have halogen branches coming off of the chain. So chlorine, fluorine, bromine, or iodine branching off. And so all of these rules are the same, except that rather than just having alkyl branches, such as isopropyl, methyl, etc., you will also have to deal with halogen branches. So our halogen branches are going to be named as the following. So we're going to name our halo branches or halogen branches as we'll start from the top. A fluorine branch is referred to as a fluoro group. A chlorine branch is referred to as a chloro group. A bromine branch is named as a bromo group, and an iodine branch is named as an iodo group. We will follow these other guidelines here exactly as they're written, and the halogen branches do not in any way take priority over any other type of alkyl branch. We'll always follow this guideline that we start numbering the chain from the end closer to where a branch comes off, regardless of whether that branch is a halogen branch or an alkyl branch coming off. When we go to place the names in alphabetical order as prefixes at the beginning of the molecule, we'll still list those in alphabetical order, and we will mix and match whatever alkyl branches we have with whatever halogen branches we have, putting those all in alphabetical order overall. So these guidelines are exactly the same as they were for naming alkanes, with the exception that now you do need to remember what the different names of the halogen branches are. So based on this information, let's go ahead and do an example problem or two here to illustrate our knowledge of naming molecules that have one or more halogen branches coming off of the parent chain. So let's take a look at this example problem here in the lower right corner, where we are tasked with developing the IUPAC name of this molecule. And since we do see wedges and dashes appearing, that indicates to us that we can also specify the stereochemistry of any chiral centers within the molecule. So first things first, we're going to go through this quick start guide to alkane nomenclature, now adapting it to include halogen branches coming off of the parent chain. So find the longest carbon chain. That longest carbon chain, I'm going to go ahead and map out here in blue highlight. So that's step one, finding the longest carbon chain to assign the parent name. We count the number of carbons in that longest carbon chain to come up with the parent name, and hopefully you come up with a total of 7 carbons in that longest carbon chain. So our parent name based on 7 carbons in the longest carbon chain is heptane. So we're going to go ahead and fill in heptane as the parent name of this molecule. Then we have to specify the branches coming off and where those branches are located in steps 2 and 3 of our quick start guide. So we have, depending on which way we number, a chlorine branch coming off at carbon number 2 of the chain if we start numbering from the right, or if we start numbering from the left, we have a methyl branch coming off at carbon number 2. So the way that we decide which method is correct for numbering is that we start numbering the chain from the end closer to the branch name that comes first in the alphabet. So chloro comes before methyl in the alphabet, and therefore we're going to start numbering from the right-hand end of this molecule. So we've got a number from the right-hand end. Go ahead and plug in all my carbon numbers 1 through 7, and then we're going to specify where those branches are located and what they're named here at the front of the name. So at position 2 we have a chloro group, at position 6 we have a methyl group, so we'd refer to this molecule as 2-chloro. And remember, always separate numbers from letters with dashes. 6-methyl, and the term methyl and heptane are just going to run together there as one word. So that takes care of naming the molecule without the stereochemistry specified. You will also notice that we have one chiral center where we can specify the RS stereochemistry because we have wedges and dashes shown there. And at that chiral carbon, we need to go in and indicate what its chirality is. Remember, we'll put that chirality designation at the very front of the name in parentheses. And if there's more than one chiral carbon, we need to specify where that chiral carbon is that we're identifying as RS, such as 2R or 2S. If there's only one chiral center in the molecule, such as is the case here, it is okay to omit the designation of where the chiral center is. So we could just call this R or S, 2-chloro-6-methyl-heptane. I will totally accept it either way. If you want to call it 2S or 2R, 2-chloro-6-methyl-heptane, that's fine. Or you can just use R or S there at the front, either or. Okay, so in order to come up with R or S, we need to rank the 4 groups that are directly bonded there to our chiral carbon. Remember that there is the omitted hydrogen atom that is a dash. We will show going back to fill in the last part of the tetrahedron. Then we rank these 4 groups based on atomic number. Chlorine has a higher atomic number than does carbon or hydrogen, so chlorine is going to be ranked number 1. And hydrogen has the lowest atomic number of the groups we're comparing, so it's going to be ranked number 4. Then to assign the relative rank of the 2 carbon atoms that are bonded there, what we will do is we will look at those carbons and ask what each one is bonded to. So this carbon on the end, we ask what it's directly bonded to other than the chiral carbon. So that carbon is a CH3 group, so it's directly bonded to 3 hydrogens. So I'm going to put C and then in brackets HHH to indicate what it's bonded to. This carbon, the other carbon that we're comparing that methyl group to, is directly bonded to 1 other carbon and bonded to 2 hydrogens. So we go ahead and plug that in. Now we compare the 2 based on atomic number. Looking at what's in the brackets, we compare a hydrogen to a carbon. Carbon has a higher atomic number than hydrogen, therefore that direction going toward the carbon atom wins. So we're going to rank that as number 2 since we already assigned the chlorine atom as number 1. Then number 3, the last remaining part there, is the methyl group. So fortunately for us, the hydrogen is oriented away from us. So all we need to do now is go from 1 to 2 to 3, determine whether that's clockwise or counterclockwise. Remember that clockwise indicates R, counterclockwise indicates S. And so here we're going counterclockwise to go from 1 to 2 to 3, and therefore we can specify this chiral center as the S. So we're looking at the S enantiomer of 2-chloro-6-methyl-heptane, and it is fine there since there's only one chiral carbon to just put S, or you could alternatively put 2S. That's totally fine as well. So in the follow-up segment to this, what we will do is go through a couple of additional example problems of naming haloalkanes, getting into some more complex examples in terms of picking out the carbon chain that's longest, or in terms of assigning the chirality to reinforce the concept of assigning R and S chiral centers. So stay tuned for that.